Okay, this podcast is going to go over some basic network security related topics. We're not going to go into super great detail on these topics, but we're going to talk about some things related to network security. The three main goals of network security or of security: confidentiality, integrity, and availability. Confidentiality means you keep secret information secret. Only authorized individuals can gain access to that information. No unauthorized individuals can access it. Integrity is you prevent data from being changed in an unauthorized manner. Only authorized users can make changes. Availability means that the data is available to the users when they need to get it. So the big threat to availability right now is a class of malware called ransomware. That if you click on some bad links, it will run a program that will encrypt all your files on your computer, and they want you to pay them money to get the key to decrypt them. So that's definitely a threat to availability. Some topics we're going to cover in our discussion. We'll talk a little bit about cryptography, encryption and hash algorithms, and we'll talk about some network security related topics. First thing about cryptography is it is hard. It is based on math that you don't understand, that is based on different math that you don't understand, that is based on even more math that you don't understand. And let me explain a little bit about that. I started out reading a book one time about practical cryptography or something like that, and it was going through the mathematical basics you need to understand how the crypto systems work. In the first chapter of the math, I kind of understood a little bit, but then it kept moving on to subsequently more difficult math that referenced back to the other math. And after about the ninth chapter, I was looking back like 3 chapters trying to remember what was going on. So yeah, it's not for the cryptography is not something for mathematical basic people like common people. Two, developing cryptographic algorithms is best left to professionals. You don't really want to just try to make up your own at this point. The best algorithms are publicly available and have been reviewed by tons of cryptographers, so they're known to be secure or thought to be secure. And we're not going to go into a great deal about how the algorithms work. And here's why. This is a little sketch of how AES works. So if you look at the top left corner, it says the plain text is in a 4x4 grid, and it does an initial round that goes into this first box that does some different transformations, and then it goes in the next round and it generates different keys for different rounds. And I don't even know what it does, but that's pretty much what AES does when you encrypt with AES. So that's one reason we're not really going to worry much about the mathematical details behind cryptography. Instead, what we're going to worry about is the different types of cryptography and why it's important. So how does cryptography apply to confidentiality, integrity, and availability? Well, confidentiality is the purpose of encryption. That is why we encrypt things, to keep it secret. Integrity, if you make a change to encrypted data, it will not result in usable changes to the plain text. So you cannot intercept the encrypted data, make a change, and have that change propagate back to the encrypted data. Then hash algorithms are a different type of algorithm associated with cryptography that can be used to provide integrity for unencrypted data. Basically, with a hash algorithm, you compute a hash of a file or image or text string or whatever it is you want to send without changing. You compute the hash for that, and then at the other side of the connection, whoever receives that data, they compute the hash of the data they receive, and then compare that to the hash that you sent, and that proves that the data did not change. Availability, how does cryptography relate to availability? Well, I had a question mark there. Can you think of any ways cryptography relates to availability? Well, somebody intercepts some data that contains, user credentials. They could use that information to, shut down your web server, and that would affect availability. So that's one possible way. Here's a little cartoon for us. It says, a crypto nerd's imagination. His laptop is encrypted. Let's build $1 million cluster to crack it. No good. It's 4096-bit RSA. Blast. Our evil plan is foiled. And then it says what actually happened. His laptop's encrypted. Drug him and hit him with his $5 wrench until he tells us the password. Got it. So yeah, cryptography is good and useful and everything, but as long as there are humans in the picture, you probably have some human error. Two different types of cryptography we're going to talk about: encryption and hashing. Encryption renders something hidden from unauthorized viewers. So when you encrypt the data, somebody who looks at it can't really see what it is. A question to ask is, are all hidden things encrypted? Example I give for that is base 64 encoded data. Base 64 basically takes data and includes it in base 64 encoding, which is like all lowercase, all uppercase, and all numbers. I think that's base 64. Maybe a couple of other characters in there because that only gives 62, I think. Yeah, so anything that's base 64 encoded can be decoded, so that's not really encrypted. This is the link to a page that shows you how to encrypt it and decrypt it. It says, can and should encryption algorithms be secret? I addressed that a little bit. No, it's better that cryptographic algorithms have been publicly reviewed by experts and they've agreed with its security. Just because something is secret, just because if the encryption algorithm is not shared, that doesn't mean it's good. They might be doing something terribly simple, and they just don't want to tell you what they're doing because they think that makes it more secure. But a good cryptographer will figure out how to break it if it's super easy. If you're evaluating a product or looking at something and they tell you they use proprietary encryption algorithms, you might want to run away from that product and go find something using open algorithms. What is hashing? We talked about a little bit. Hashing kind of hides something you never want to see again. That's not really what I should have put there. Hashing is a one-way function, so you cannot compute the original value from the hash. That's why it says hiding something you never want to see again. If I compute a hash on something, that gives me a string of characters, but I cannot take that string of characters and recreate the original text or document, and we use that to prove that it hasn't changed in transit or has been modified by some third party. So how does encryption work? Basically, encrypted data equals the plain text plus the key plus the algorithm. The plain text, you get the plain text back by taking the encrypted data and combining that with the key and the algorithm. XOR is a very simple type of encryption where essentially we have this plain text block of 0, 1, 0, 1, 0, 1, 0, 1, and we have a key of 1, 0, 0, 1, 0, 0, and if we XOR those two together, the result we get is 1, 1, 0, 1, 1, 1, 0, 1. If we apply the key to that again and XOR it again, that will result back in the plain text. So what happens if you encrypt the same data with the same key? Well, in this case, if you encrypt the same data with the same key, you end up with the same encrypted data, and that's kind of bad. So most of the time, encryption algorithms take some put some mechanism in place to ensure that the same plain text values do not render the same encrypted value. So it makes it harder to attack the encryption algorithm. Two different types of cryptography we're going to talk about: symmetric key cryptography and asymmetric key cryptography. Symmetric key cryptography is also called secret key cryptography, and asymmetric key is called public key cryptography. So symmetric key uses the same key to encrypt and decrypt the traffic. Key lengths are from 40 to 256 bits usually. Two types of symmetric key algorithms: block ciphers and stream ciphers. A block cipher operates on a fixed size block of data, and I've listed some examples here of different types of block ciphers. And stream ciphers operate on a stream of data, and I've listed some different streams on there. So what's the difference between a block and a stream? Well, a block is you take 64 bits of data and operate on that block all at one time, and a stream cipher operates on the stream of cipher, either a bit at a time or a byte at a time. What's the biggest issue with symmetric key cryptography? The biggest issue with symmetric key cryptography is you need to share the key with somebody before they can use the key. And how do you securely share a key with somebody that you're trying to securely communicate with? You send it to them in an unencrypted email, or do you call them on the phone? There's a problem with trying to get the key securely to the other side when you don't have a secure channel to communicate with. Asymmetric key cryptography uses two public but mathematically related keys. One of the keys is generally referred to as the public key, and one is generally referred to as the private key. And the key lengths vary from 512 to 4096 bits. But the other day in the lab, we were generating SSL certificates, and they said 512 bits was not secure. So 1024 is probably the lowest bit length you should go with at this point. So With this type of cryptography, you use the recipient's public key to encrypt the data, and then the recipient can use his private key to decrypt the data. And that makes sense because the private key is what the recipient has that no one else has. The recipient takes his public key and shares his public key with everybody he wants to communicate with, and then anybody who has that public key can use it to encrypt the data, and only the person with the private key can decrypt that data. So the person with the private key could read the encrypted data. So encrypt with the public key, read with a private key. Public key cryptography can also be used to sign data. It goes without saying that I should be the only one with my private key. So if I want to prove that I sent something, I can sign it with my private key, and then you can use my public key to verify that signature, and that proves that I sent it because I'm the only one with my private key. So if it was signed by my private key, then I'm the one that signed it. In theory, of course, private keys can be compromised, but in theory, that's the way it's supposed to work. Symmetric versus asymmetric, which one's better? Well, symmetric key advantage is it's faster, and it's strong with long key lengths, and you only need one key. And the disadvantages are you need the secret key with each party you want to communicate with. So I talked about sharing the keys. I didn't talk about the fact that if you want to do it properly, you need to use a different key with every different party you want to communicate with. Difficult to exchange keys, and it doesn't have any built-in authentication or non-repudiation. That was the signing I was talking about a minute ago to prove that the person is who they say they are. Now, you don't really get that with symmetric key cryptography. All right, digital certificates. We generated certificates in the lab where we did SSL, so this should be kind of a review for you. We generated key pair, a public key, a private key. We also generated a certificate signing request when we wanted to send it to the certificate authority. You send the certificate signing request to the CA. The CA verifies who you are and signs the certificate. So now people that trust that certificate authority can now trust that you are who you say you are, because that certificate authority verified that you are you. And I put verified in quotes because what does that really mean that they verified you are you? Well, it depends on the certificate authority, but most of the time they send an email address to some email address. Send an email to some email address that matches with the domain name you're trying to get a certificate for, and if you get that email and reply, then they consider that verified. Sometimes you can get an extended validation cert where they actually call you and talk to you on the phone and make you submit additional documentation to be verified, but the verification process isn't super strict in some cases. Practical implementation of cryptography, we use SSL TLS to secure just about anything that's done over the web. How does that work? We talked about this in the SSL lab also. It uses digital certificates to prove that the website is valid. It uses asymmetric cryptography to exchange a symmetric key, and it uses that symmetric key to crypt the data. So we talked about the problem with symmetric keys is we have to exchange the key. Well, we can exchange that key using asymmetric key cryptography. So the certificate has the website's public key in it. So the client can encrypt something with that public key, and by something it can encrypt a shared session key, which is a symmetric key, and then it sends that encrypted session key to the web server, and the web server can decrypt it, and now the web server has the session key that they can use to encrypt the actual data that gets sent between the client and server. So we talked about hashing a little while ago. Hiding something we never want to see again. Example of that is password hashes. If you look in the password database on servers, you'll see that they are strings of random looking characters and not the actual password the user entered, although a good password looks like a string of random characters anyway. So basically when someone logs into the system, we take what they enter and we hash that with the same hashing algorithm, and then we store that with the we compare that with the stored hash we have in the password database. And if they match, those hashes match, we know that was the password the user entered, and we let them into the system. We also mentioned how we use it for integrity to make sure something didn't change when it was sent. And then we talked through some different hash algorithms. The main hash algorithms you run into are SHA and MD5. So now we're talking a little bit about network security. We've been working with routers up to this point. You can add some amount of network security on routers by using access control lists. You can allow or deny the traffic to flow based on different parameters. Standard access control lists can filter based only on source IP address. So using standard ACLs, you can't provide very granular levels of control. Extended ACLs can filter on protocol, source, destination IP address, and ports, and other things. So we're going to be working mostly with extended ACLs in the lab. A firewall is basically, in most cases, a router with special software to allow filtering. What's the difference between a router with ACLs and a firewall? Well, depends on what router you're using and how well it supports ACLs, but usually the firewall does more advanced things like stateful inspection, allows for some application level inspection as well in some cases. And ACLs on routers usually just look at the packet parameters without much intelligence built into the filtering. So some topics we should be aware of with firewalls. Network address translation, we've talked about this, we've done this. This is where we translate our private IP addresses to a public IP address so the traffic can go to the internet. Firewalls almost always do that. Access lists, I've listed that as a standard ACL. Packet filtering, I've listed extended ACL. So remember, if you remember, standard ACLs can only filter based on source IP address, whereas extended ACLs can filter based on many more packet parameters. So we call that packet filtering. Stateful packet inspection, that's where the firewall or device keeps track of the state of the connection and only lets traffic in that matches the state. And what do I mean by state? Well, we should know that a TCP connection starts with a three-way handshake. So we send out a SYN, we see it SYN ACK come back, and then we send out an ACK. After we do that, the connection is established. So stateful packet inspection doesn't allow packets in if they're not in their proper state. So if I have not sent a SYN packet out, then a stateful firewall will not let a SYN ACK back in. If I haven't completed a three-way handshake, the firewall would know that there's no active session. So if somebody tries to send a random packet back in, the firewall won't let it in because there's no session established. Application layer inspection, that's where the firewall looks at the actual details of the things going on at the application layer. A good example of this would be for like an FTP connection. FTP, you can do puts or gets to get data or put data out. A common thing you might allow people to download things using FTP, so they can do FTP gets, but you don't allow FTP puts because you don't want them sending data out of your network. So that's a common example of when you might do application layer and what might happen with application layer inspection. Some more firewall related topics. The demilitarized zone is an area of the network that allows external users to connect. So generally you don't want to let traffic from the outside straight into your internal network where all your users and all your servers, all your sensitive data are. You make those outside users connect to a special area called a DMZ. A couple different ways you might implement a firewall that we're going to do in the lab. Routed mode, the firewall is a hop in the network and provides routing functions. So the firewall also works as a router. It has a routing table. It can use routing protocols to exchange routing information. And this is the most common configuration you'll probably run into. And then transparent mode is way where a firewall can work like a layer 2 bridge. Basically, the term you might see is a bump in the wire. So the traffic flows through the firewall, but the firewall doesn't take the packet apart and put a new IP header on it. It just bridges between the two interfaces, but it does decompose and inspect the traffic, and you can make filtering decisions based on the layer 3 or layer 4 information. And the main benefit of a transparent mode firewall is if you have an existing network that you don't want to make any network changes to, you can just stick to transparent mode firewall in the middle of the connection, and you don't have to change any IP addresses or anything on your network. Intrusion detection prevention lets us look at and block malicious activity on the network. So an IDS will just monitor and alert on the suspicious activity. An IPS can take the next step of blocking the malicious activity. When I was working back in the real world back in the day, we were kind of scared of turning on the IPS functionality because we didn't want just automatically blocking a bunch of stuff. But these devices have matured a great deal since then, so most people actually do have some form of prevention where they're blocking some of the malicious activity. A couple of different types of intrusion detection and prevention. There's host-based versus network-based. Host-based runs on the individual host computers and affects traffic coming to that host. And network-based is something on the network. It might be built into the firewall, or it might be a separate device that's looking at the traffic, and it's blocking the traffic based on matches to whatever algorithm the device uses to detect malicious traffic. Which should you use? Well, if you got enough money, use both. Use host-based and network-based. If you don't have enough money, you have to look at what you're trying to protect. Are you trying to protect everything or just your important host? It might be more cost-effective to go with host-based if you're only looking for protecting your most valuable host. Signature-based versus anomaly-based. Signature-based essentially has a dictionary of signatures, and it matches known bad things, whereas anomaly-based looks at patterns in network traffic and tries to detect bad things based on things that don't look normal. Any questions, post them to the discussion board or bring them to class.